Morning, students. Today, AICTE PRERANA scheme for preparing SC and ST students for higher education. In this section, we discussing about the subject chemical reaction engineering. From chemical reaction engineering, we discussing under the topic what is reactor, and from reactor we have several types. After from several types, we have to design how to design a reactors. Okay, I am. And before that, introduce myself. I am G.V. working as an assistant professor in chemical department, chemical engineering department, Erode Sengunthar Engineering College, Perundurai. Um, in here, you have to know what is reactor. Okay, so before we have to see discussing about reactor and what is the purpose, we have to know. So in reactor, the purpose is the reaction can be happened, the reaction can be take place in reactor. So that is the purpose for reactor. Okay, so we can't easily taken as reactors. So here the application for reactor. Okay, so application of reactor means we have n number of industrial applications, like any manufacturing or any productions. We have n number of application is there. So before in applications, we have to know the basic concept and what are involving the what are the involving factors, and then how to design in efficient manner and to obtain the high conversions. So all those things we have to discuss in this class. Okay. So in industrial, all the manufacturing process we have, and in we have from any manufacturing process it happened two ways, like unit operation and unit process. Okay. So in unit operation, we divided into category, that is based on separation and based on physical properties. Okay, so physical properties means here they clearly mentioned, like cleaning purpose, filter purpose, like all those things. But in second one, separation purpose means among three phases we have gas, liquid, solid. So from three phases, if any productions or in any manufacturing, it involved two phases or two phases. So among the two phases, from productive oriented, we need to separate. So that is in separations. So after the unit operation, here involving the unit process. So unit process means it happened in chemical process alone, that is chemical changes alone. Okay, so from chemical changes means it mainly deals about in chemical reactions. Okay, so from chemical reactions, in chemical reactions, we have based on chemical reactions. Based on chemical reactions, here number of variation is there. Because generally we have viewed as many category wise, like homogeneous reactions and heterogeneous reactions, and then reaction can be carried out in series and parallel, like exothermic reaction, endothermic reaction, and then reversible, irreversible reactions, and then catalytic reactions and non-catalytic reactions. Like we can classify the several types for these reactions. So in this reaction, the chemical changes can obtain by using the reactor, by using the reactors. So from reaction, how we can the chemical changes, how we what the changes can be occurred, like how to optimize, how to calculate, like means so that process we can term as chemical kinetics. Okay, so in chemical kinetics means it deals about normally the chemical kinetics it deals about the rate of reactions. Okay, so the rate of reaction, how we can define the rate of reaction means like generally we can term as the rate of reactions with respect change in concentration with respect to time. That is, we in change in concentration means normally in reaction reactor is the and after before on the left hand side, I think all of you know how to represent the reaction. Okay, so from representation of reactions or any manufacturing, for example, we can take. So in reactions, that is the left hand side reactants. Okay, so the left hand side reactants, in between the right side we can take as product. In between the reactant and the product, the arrow mark here we can mention. So through the arrow mark mentioned temperatures, whether the temperature can be carried out in a constant manner or varying manner, and then pressure, and then catalyst, whether it is a catalytic or a non-catalytic. So all those purposes we have to mention in between the reactant and product in aside of aroma. Okay, so these are the common nomenclatures involved in chemical reactions. Okay, so from this reaction, we have to determine the rate of reactions. So from the rate of reaction, generally we can define that is change in concentration with respect to time. So from this definition, we can mathematically write as minus RA into like a proportionality into dCA by dt. After then we can expand that expand that now. Minus RA equal to K into CA. That is the minus RA equal to the minus RA equal to the minus RA equal to K into CA. Okay. So here the minus of RA denotes the rate of reaction. So why here indicating negative sign means because the disappearance of the reactants. Okay. So and then the K term denotes the rate constant. Okay. So after then CA, that is the CA denotes the concentration of the reactant. Okay. So from the mathematical term form in rate of reaction, so the constant term, that is the K can denoting the rate constant. So from the term, the ultimate is to calculate the rate constant. Okay. So how we can calculate the rate constant? Okay. So from these all those, so from these all those, we have to varying. Further, they can be classified as further we can classify it as a rate constant. So here involving the term order of reactions. Okay, so from order of reactions, how we can define this? That is the sum of the power of the concentration terms. Okay, so it is possible to determine order of reaction for all the reaction is not possible. So Through this not possibility, so we have five methods to determine the order of reactions. So through order, determine the order of reactions. So the first method is differentiation method, second one is integration method, and the third one is isolation method, and fourth one is Oswald dilution method, and fifth one is half-life period. Okay, so from half-life method and Oswald dilution method and then isolation method, it's not convenient to use. Just it one of the method, and if we calculate, finally the answer will be appropriate answer. Okay. Um, so after from five methods, the three methods is doesn't give approximate answer, and then it does not follow for many reactions to calculate the order of reactions. Okay. So after then we have two methods like differentiation method and integration method. Okay. So from differentiation method, finally the derived form of answer. Okay. So finally what we determined in the answer can give approximate answer or no. Does it give appropriate answer? So this is the reason finally we from five methods they focused along in integration method. Okay. So through this integration method only we have to derive and derivation form first order reaction, second order reaction, third order reaction, and pseudo first order reaction, and like a zeroth order. So all those reactions we have to derive from integration method. From this reaction we have to derive like two types of reactions, reversible and irreversible. Okay. So after the through integration method we calculate the derivations, the derivative forms for respective orders. Okay. So this all and all the fundamentals for reactions. Okay. So finally, in reactors, the reaction can be carried out. Okay. So we have several types of reactors. Okay. So the first one is batch reactor, and then second one is semi-batch reactor, and then third one is continuous reactors. Okay. So that is the batch reactor means uniform compositions. That is the composition can be in uniform, changes with respect to time. Okay, that is the batch reactor. And the semi-batch reactor means like it can be followed like pseudo first order, like one reactant will be added in simultaneous manner. Okay, so that is called the semi-batch reactor. And then third one, continuous reactor. So in continuous reactor, they can be divided to categories like mixed flow reactor and plug flow reactor. So otherwise, the mixed flow reactor we can term as continuous stirred tank reactor. Okay. So in MFR, that is in mixed flow reactor, we can say MFR also. So in CSTR reactor, that is continuous stirred tank reactor, the uniform, that is the mixing can be happened uniformly. Okay. So at the time, okay, so the reactants, that is in reactor, the reactants can be changing the same compositions. Okay, so at simultaneously releasing the product also. So that is called as mixed flow reactor. Okay, so and then in plug flow reactor, flow of fluid. Okay, so the flow of liquid can be give. Here doesn't happen, the mixing doesn't take place. Okay, so here which fluid can be give the input. Okay, so after the reactions it happened, it releasing the product. So here in plug flow reactor it doesn't take any mixing or any external forces, so all those things. So basically these are all the types of reactors. Okay, like batch, semi-batch, and continuous. So from this continuous, maximum they used flux to flow reactor, flux to flow reactors. So maximum here it involved continuous tank, that is the flux to flow reactors. And we have at the current results they implement a number of reactors, advanced type like photochemical reactors, sonochemical reactors, like okay. So next we enter into reactor design. Okay, so if you design a reactor, we have to find out what are the parameters, that is what are the factors, what are the parameters involved in the reactors. Okay, so in reactor all of you know concentration is one of the most factor parameters, and then temperature, and then pressure. After then we doing the kinetic studies. Okay, so here mentioned the 6 point. So it's common for concentration, kinetics, temperature, pressure can be involved in reaction and the reactor. Okay, so here the volume and volume also involved here. So for we can taken for a mixed flow reactor means we can taken as a uniform volume and constant volume. Like for example, the fluid reactor is it can be varying. Okay. So flow rate here mentioned, what is a factor and which factor here what here mentioned. So in reactor we can feeding the reactors like in basics of flow rate allows. Okay. So these are the 6 parameters involved in reactor design. The first one volume of reactor, flow rate and the concentration and the kinetics and the temperature and pressure. So in mixed flow reactor and plug flow reactor, we can say the residence time, mean residence time. Okay. So before that, residence time, mean residence time, or like before we know what is ideal reactors and non-ideal reactors. Okay. So from ideal reactors means the in reactor the reaction, all those things can be carried out in constant manner and a smooth manner. That is we can term as ideal reactor. But in non-ideal reactor means either the reactors in reaction it can doesn't obey the so the non-ideal reactors means in reactor the reaction can the flow patterns doesn't occur, or either the time variation can be occur, like the mixing doesn't happen the uniform mixing, or else the flowing for one reactants to another reaction in the reaction it doesn't happen. Either one reactant can be stored in under the stagnant positions. Okay, so like all those factor we consider as non-ideal reactors. Okay, so in ideal reactors means we can able to find out all those factors like rate of reaction or kinetic studies, or to determine the concentrations, like all those. But in non-ideal reactor means it is difficult to calculate the rate of reactions, concentration, all those factors. So at that time here involving the term residence time distribution. Okay, that is we can term this RTD. Okay, so RTD means that is a residence time distribution. So So how we can call the residence time distributions? In reaction, it can be in reaction the reactants uh, component A and B can be take place. At that time, it can be resident. That is, resident means it can take uh, the reaction can happening in slow and to settled and to residate. Okay, so after the mixing process can happening, that is distribution can be happening. So like all those steps are following in any reaction at the process, and then at the term we can term this residence time distribution. Okay, so through this RTD residence time distribution, we can't directly able to measure the concentrations. Okay, so first we have to determine the RTD. After then we go into determine the concentrations. Okay, so we have many method to determine the concentration like RTD. Yes, we have two methods: step input method and pulse input method. Okay, so here from basics of step input method and the pulse input method. From a step input method, we calculating the E curve, and then pulse input method we can get the F curve. So from by relation between the E curve and F curve, we have to calculate the C curve. Okay. So the curve that is E curve, F curve, C curve, that is under we can convert from one curve to another curve, easy to convert. So this is the basic difference for ideal reactors and non-ideal reactors. Okay. So now that plug flow reactor, mixed flow reactor, like in design purpose, so we have to apply we have basically two balance. Okay, mass balance, energy balance, material balance, three types. So here we in mixed flow reactors, we have to do mass balance. Okay, that is capital V. Okay, for capital V volumetric flow rate divided by FA naught means feed input. Okay, so equal to we can write time, that is residence time by concentration, and then in similar we can write an conversion by change in conversion by rate of reactions. Okay, and then here tau indicate the residence time. Okay, so residence time mean residence time. Okay, so and then like in plug flow reactor. Okay, so same as P by FA naught equal to T by CA naught equal to. So here that X A by minus RE. Okay, this is for plug flow reactor. So in here, plug flow reactor and mixed flow reactor. So through this plotting for graph between the conversion and rate of reaction. Okay, so through conversion and rate of reaction, so through this area. Okay, so that area number of box, that is number of squares from graphical method. Okay, so that number of squares into x-axis into y-axis, that is we determined as area. So that area we can denote it as tau, that is mean residence time. Okay, so from graphical method, this is one of the method to determining the residence time. Okay. So here for based on the orders, okay, for based on the orders, the performance equation can be varying. For example, here the order can be in zeroth order. The rate of reaction we denoted as K. Okay, so how we can write in two types of reactors, like plug flow reactor and then another one mixed flow reactor. Okay, and then if if the order can be in first order, the rate of reaction we can write as minus RA equal to K into CA. Okay, so here the performance equation can be involving in terms of conversions. Okay, so that is the K into tau. So rate constants into tau, that is mean residence time, equal to ln of 1 by 1 minus xa. But here the xa by 1 minus xa. Okay, here ln can be the in mixed flow reactor doesn't come ln. I can rate order of reaction is to we can write as the rate of reaction minus RA equal to K into CA square. Okay. So and then if the order of reaction is in nth order, the performance equation can be right in blood flow reactor n minus 1 into Ca naught power of n minus 1 K tau equal to again we terminate again we can derive into concentration terms Ca by Ca naught into 1 minus n minus 1, that is equal into derive into conversion, that is 1 minus Xa into 1 minus n minus 1. Okay. Here, one more type of reactor, that is autocatalytic reactor. Okay, so here, at which condition we can term this autocatalytic reactor? Means, like in reaction, the reaction can be carried out in the presence of catalyst. Okay, so at the catalyst, it doesn't act like catalyst. While the conversion of product, okay, so while the conversion of product, at that time the catalyst can act like a product, we can term this autocatalytic reaction. So for this purpose, in autocatalytic reactor, it doesn't happen for recycle purpose. Okay, and then it have low percentage for recycle ratio, and then the product concentrations can be in minimum. Okay, so from these reasons, in autocatalytic reaction, we have to mainly focused to optimize the recycle ratio. Okay, so after the design of reactors, that is the reaction can type as parallel reaction and series reactions. Okay, so here the A is the product, sorry, the A is the reactant. Okay, it gives the product two simultaneous wave. So here in two simultaneous wave, that is the required here or is the desired product, required product, and here S is the unwanted product. So from these two product in between the rate constant value is there. Okay. So what is the purpose for a parallel reaction is? So to get maximum amount per desired product. Okay. So from this reaction, so from this parallel reaction, we can, in terms of rate of reaction, that is for a small or suffix capital R equal to, that is rate of reaction for product R equal to dCr by dt. Okay. So from dCr by dt, we can expand into K1, that is rate constant into Ca into A power of A1. Like we have write the unwanted product also. So from basic in parallel reaction, we have to write the rate of reaction in desired product and unwanted product also. Okay. So first this is the equation for the desired product, and then second unwanted product, like Rs equal to dCs by dt equal to K2 into Ca power small a2. Okay, so we can simplify both the desired product and unwanted product. So that is equal to K2 by K1 equal to Ca power of A1 minus A2. Okay, so these are the cases. Okay, so the three cases can happen in a parallel reaction, like the concentration of component A and the component B can both the reactants can be added in high manner, or else the both the reactants, the both the concentration of the reactants can added in low manner. And then third case, the concentration of the component, one component can be added in a high amount and another component can be added in low manner. So these are the three cases for improving the contact patterns. So after that, multiple reaction, that is series reaction or multiple reaction. Okay, so this is the representation for the multiple reaction, that is A is in the reactant and it gives the R, and simultaneously it gives the gas. So between the rate constant. Okay, so the basic difference from multiple, that is series reaction and parallel reaction is, in parallel reaction it can happen with the desired product, formation of desired product and the unwanted product. But in here, series reaction, it can form the intermediate product. After that, it gives the intermediate reactant. After that, it gives the desired product. Okay. So these are all the basic examples, like a parallel reactions and the series reactions. That is the halogenation of alkane. So here, in series reactions and the parallel reactions, the contacting pattern is very important. Okay, so from contacting pattern only, it can release, it can easy to obtain the high conversions. So based on these contacting patterns, We have three cases, okay, based on the conducting pattern. Okay, so by the case one is add A, add the component A slowly to B. That is the component A alone here adding these slowly, but here the component B can be added. So the schematic diagram for this case one here. Okay, so from this case one, the contacting patterns, whether it is involving or not, means it can be involving, and the mixing can be very high in manner, because here on the reactant is constant. Okay, so and another reactant can be adding in limiting manner. So that is why here the mixing can be take place in uniformly, and mixing can be take place here uniformly, and the concentration also we can obtain at a higher rate. Okay, and then the case 2 is add B slowly to A, like vice versa. Okay, here the component can added, the component B can be added in the beaker of A. Okay, so this is case 2. So here what will happen means the intermediate, that is the desired product and undesired product, can be happened here. Okay, so and then here case 3, the component A and B can added, both the component can added here simultaneously. So here both the reactant or both the component can added in simultaneously. So here the uniform mixing can be high, and recycle ratio also obtained in high increasing manner. Okay, so next moving into residence time distributions. So it is one of the important factor from the point of view of real equipment. Okay, so already I told basically in reactors we have ideal reactors and non-ideal reactors. Okay. So here the ideal reactor design are made by many considerations like a volume of reactor, or else time spending by the reactant, and then after releasing from the product, and spending by releasing the product. So after that, whether the reaction can be take place completely, can be take place, or else whether here any accumulation can be happened, or else stagnant, like all those factors. So therefore the distribution of time inside the reactors we call as capital E, that is the exit age distribution. Okay, so what I told, the factors like stagnant positions or some short circuiting, and then whether channeling happened. Okay, so those are the reasons happened any reaction in the reactor, like stagnant position or any short circuiting or channeling, uniform mixing, contacting patterns, like all those factors can be happen in the reactors. We can do this on ideal reactors. Okay, so we can't easy to determine the residence time distribution. So from residence time distribution, we can determine by two experimental method. That is the pulse input method and step input method. Okay. So in pulse input method, can be carried out under the steady state, and in pulse input method, experimentally we have to insert employ the tracer, so the tracer will able to determine the concentrations. Okay, so based on the tracer, we can the output can be optimized in the pulse manner graphically. Okay, with the basis of variation with respect to time. Okay, so here the from a pulse input method. Okay, so from pulse input method, experimental here. So uh, the graph between time and concentration pulse. Okay, so here we have to determine from pulse input method. We determine the E curve. Okay, so the areas we can the peaks. Okay, the areas we can count as number of squares. Okay, so based on the peak levels, based on the number of squares, that is equal to integral of 0 to t c into dt. So in other ways we can write as summation of ca into time intervals. Okay, so from pulse input method we can able to determine the e curve. Okay, so and then another method is step input method. So like step input method also happening, but like in step input method compared to pulse input method, the step input method will give accurate answer. Okay, so after the residence time, in non-ideal reactors, they can be based on the time factors. It can be divided two types: holding time and residence time. Okay, so holding time and residence time. So in a holding time, what is how we define the holding time? So the time in any reactor. Okay, so in any reactor, it have a uniform volume, that is the constant volume. So at that time, the constant volume in a reactor, the reaction can be happened. Okay, so that is called the holding time. So from starting up to now, what we discussed means that is in a homogeneous in, in sheet of reactors, all those can be occurred. Okay, so next we move into heterogeneous. So based on this heterogeneous, they divided under two categories: catalytic and non-catalytic. Okay, so here also temperature, pressure, concentration, volume can be involved, and apart from these factors, the heat transfer and the mass transfer also involved in here. In here, the heterogeneous reaction. Okay, so in heterogeneous reactions, normally the reactions have a mechanism. So in mechanism, we have in homogeneous, the mechanism can be followed initiation, propagation, termination, like. And then in heterogeneous also not like the mechanism steps. So it have the 5 steps in heterogeneous process. So from 5 steps in heterogeneous process, that is the first step, uh, the transportation of fluids or transportation of reactant from bulk. Okay, bulk phase. After the bulk phase, the second one can be adsorption process. Okay, so after the second step adsorption process, move into surface controlling. So and then surface controlling, fourth one is desorptions. Okay, so and then fifth one, next we move into desorptions. Next, whether the recycles. So the how important mechanism in heterogeneous. Okay, heterogeneous mechanisms, reactions. So like in homogeneous, in heterogeneous also, from different mechanism we have to calculate we have to do kinetic studies. In kinetic studies means like same similar, like we have to write down the reactions. After then we have to rate of reactions and the kinetics. So all those we have to measure, determine. Okay. So here based on the heterogeneous catalytic system and the non-catalytic system. So on catalytic system means we can catalytic system, it can be as usual same classification, plug flow reactor and mixed flow reactor. Okay, so in plug flow reactor we have two types, a differential reactor and the integration reactor. Okay, after the plug flow reactor, the second type is mixed flow type. So in mixed flow type we have fluidized bed reactor. Okay, so through this fluidized bed, in design factor we have to consideration. So what are the factors we have to do consideration? First one, what is the reaction type? Second one is reactor, and third one economics, that is financial economic. So determine like operating cost, right? After then rate of deactivation, and suppose in any reactions it need another process like. So, what I mentioned from 5 on, so we have to discuss. Okay, so from reaction type, first we have to know which type of reaction, either series or either parallel, reversible or irreversible. Output. And then second one, other the reaction it's take place under exothermic or endothermic. Okay, and the third one, suppose the reaction can you need to proceed catalyst or not. Okay, so and then fourth one, temperature, reaction temperature. From catalyst, whether we employ which type of catalyst. Okay, so these 5 points are important to keep an important reaction. And then reactor means second one, reactor type means in reactor we have plug flow reactor and mixed flow reactor, or else a batch and semi batch like. Okay, so in reactor types, what is very important is contacting pattern, very important. And then after then, suppose it can be required any heat energy. So suppose it have any heat energy means it required any heat transfer rate, like all those factors. Okay, for example, suppose the heat energy required means fluidized bed, and then mass transfer. If you have a high mass transfer, so that is packed bed reactor very used. And the third factor, economics. That is economics like means in financial. Okay, so mainly the reactors have to focus depends upon size. Okay, so in reactor also like reaction series parallelly it happened. Like in reactor also we have to instead to different size, whether carried out in series or parallel. Okay, so after then catalyst purpose. Basically the catalyst is not inexpensive. It's not inexpensive. That is, it's not in very costly. And then ability to regenerate in a process for catalyst. Okay. So for economic wise, uh, reactor and catalyst for both the point we have mining. So like several types of reactors in heterogeneous system, packed bed, fluid bed. Okay, so from packed bed means normally the contacting phase is solid and fluid. Okay, so through packing we using a high amount of packing materials like at least here pressure drop doesn't occur. In fluidized bed, pressure drop is minimized low, and then in fluidized bed catalyst can able to regenerate, and the amount of catalyst also very less. So all those factor in fluidized bed. Okay, so in fluidized bed based on catalytic reactor design, it can be four types: bubbling fluidized bed, turbulent fluidized bed, second one, third one fast fluidized bed, and the fourth one finally pneumatic conveying bed. So from fluidized bed, we have to improving the contacting times and pressure drop. After the pressure drop, whether the porosity, that is pore volume, void can be occurring or not, and after then velocity. So all those parameter we have to check it. Okay. So here bubbling fluidized bed. Okay. So in bubbling fluidized bed, from design factor, we have several methods, five methods. From five methods, the first one is dispersion and tank series model. Second one, a hydrodynamic flow model. And third one, KL model for bubble fluidized bed. Fourth one, RTD, residence time distribution and contacting time distributions. So now enter into non-catalytic system. So here the non-catalytic system is doesn't in a reaction involved with the catalyst. Okay. So at that time, while the catalyst cannot be involved in heterogeneous and then in non-catalytic system. So at the conditions, we have to do heat transfer and mass transfer coefficients. Okay. And then contacting patterns is important. So after then the solubility also we have to focus. So from this solubility, it happened any equilibrium or non-equilibrium positions. So through non-catalytic system, we have two based on two models. For example, non-catalytic system, the heterogeneous phases either fluid or fluid or solid to gas. Okay, so from these phases in a non-catalytic system, we can classify it as shrinking core method and sinking core method and progressive core method, PCM and SCM. So examples of non-catalytic, like burning of coal. The burning of coal means it happened exothermic reactions, carbon and O2 can be forming the carbon dioxide plus heat. So from this reaction for a shrinking core model, it classified three. The mass transfer occurring can be three steps. That is flame above the core, and after burning ash layer can be forming, and after ash layer the resistance, the ability to do the chemical reactions. So from three steps we have to do the we have to determine the residence times. Okay, either in spherical particle or cylindrical particle by changing the size or unchanging the size. Okay, so thank you. Remaining we can discuss from next classes. Thank you.